Hey kiddos, welcome to lesson number 3. Today we are going to continue our discussion of wave-particle duality. So last class we were talking about how the photoelectric effect was evidence that light could act like a particle, right? Can a particle also act like a wave? And so we'll look at the criteria in which a particle could act like a wave, and we'll talk about the probability with which we know a particle's position or speed when it's acting like a wave. All right, so again, we're talking about a photon being a light particle. So in the past, we've been talking about light acting like a wave. It could reflect, refract, diffract, and interfere. But in the photoelectric effect, photons were undergoing collisions with electrons. It was acting like a particle. But a photon has energy but no mass. So that's problematic because if we wanted to find the momentum of a photon, we can't use our standard equation P equals mv, right? Because a photon has no mass. Right, and it's always traveling at the speed of light, which is 300 million meters per second. A way that we've gotten around this is using the equation that momentum is equal to a photon's energy over its speed. Okay. Joules over meters per second still give us the same units for momentum. And so we can use its energy, which is the energy of a photon is Planck's constant times its frequency, and we divide that by the speed of light, the specific speed. All right. Okay. And if frequency over speed is wavelength, so that means Planck's constant over wavelength is how we can calculate the momentum of a photon, right? So this is typically how it is written, and I think that's how it's written in your data booklet. H over wavelength is the momentum of a photon. Okay. Now there's a scientist named, I'm gonna butcher his name quite frankly. He's a French scientist. I will call him de Broglie because I can't pronounce de Broglie. I can't do it. So you say it like French. So go ahead and try if you'd like. I'll just say de Broglie. Now there's de Broglie was doing research on under what circumstances can a particle act like a wave? So can we get a beach ball or a marshmallow or an electron to act like a wave? So he assigned wave-like properties to something that is normally thought of as a particle. So if we have our equation for a photon, momentum equals Planck's constant over wavelength, then we could write that as wavelength equals Planck's constant over momentum. But if we have a particle with mass, we can calculate its momentum by multiplying mv, right? And we can take that and substitute it in there. Okay, and so we can end up with a particle with a mass can have a wavelength that's equal to Planck's constant over its momentum. So we could calculate a wavelength for a particle with mass using the same equation that we used for finding the momentum of a photon that has no mass. But when do we treat something like a particle and when do we treat something like a wave? Well, for something to act like a wave, it must reflect, refract, diffract, and interfere like we've been talking about. And if you had a particle that's acting like a wave, or anything, right, any wave that's acting like a wave, we know for it to diffract, the aperture size that wave is going through has to be on the same order of magnitude as the wavelength. So this is a condition for diffraction. If we get a particle to go through a certain aperture going a certain speed, can we get an interference pattern? And that's kind of the question. So let's do some calculations, and then we'll actually see if we can make this happen. So my first question is, can you find the de Broglie wavelength of an electron moving at 10 to the 5th meters per second? Okay, so we've got our wavelength is equal to Planck's constant over mv, where this mass is the mass of an electron, which is, okay, so Planck's constant is 6.6 times 10 to the negative 34. Mass of an electron is 9.1 times 10 to the minus 31 kilograms. And the speed of that electron is 10 to the 5th meters per second. Okay. So if an electron was going this speed, it would be acting as though it had a wavelength of 7.29 times 10 to the negative 9 meters. Huh. It's like on the order of nanometers, 7.29 nanometers. So could we get it to diffract? Right? What sort of thing, what sort of object, is there anything that has a spacing that's about that order of magnitude that we could shoot an electron at and maybe see an interference pattern, get some diffraction to happen? Well, it turns out a crystal has an atomic spacing of about 10 to the minus 8 meters. Okay, so that's what de Broglie tried, and see if we could actually see a visible diffraction pattern. Okay, so we'll try that out in just a second, and I'll show a demo that's produced by a scientist at the University of Oregon. Let's try one more thing. Could we find the de Broglie wavelength of a proton that's accelerated through 500 volts? What? Okay, so we're trying to find the de Broglie wavelength, right? H over mass of the proton times speed. What we need to figure out is the speed. We don't have that information, but we've got the voltage. Conveniently, though, we know that charge times voltage is equal to 1/2 mv squared, right? If you can take a charge, expose it to a potential difference, and that will change the kinetic energy. So the charge that we're going to talk about here is the charge of the proton, and this mass is the mass of the proton. So we can just plug and chug. And you end up with a speed that is 3.1 times 10 to the 5th meters per second. Okay, you can prove to yourself that that's how fast that proton will go when experiencing a 500 volt potential difference. Okay, then we go plug that in up here to our wavelength equation. Wavelength is equal to 1.3 times 10 to the minus 12 meters, right? So we can see that something that's more massive, like a proton, seems to have a smaller wavelength. Okay, all right, how fast was that electron going? 10 to the 5 meters per second. This proton is going 10 to the 5 meters per second. but it has a much larger mass than an electron, and so it has a much smaller de Broglie wavelength, or a wavelength that it would have if it acted like a wave. All right, so let's try and get specifically an electron as a particle to act like a wave. Okay, so we need to accelerate it up to some speed, right? We used 10 to the 5th meters per second in that previous problem. How would we get an electron to go that fast? Well, just like we got that proton to go that fast, you have to get an electron. You can't just like go to an electron store and buy an electron. You have to free the electron from a material. So we're going to heat up a filament. We're going to heat up a piece of metal, a piece of wire. And when it gets hot enough, the electrons are free, and then we'll expose that to a potential difference. And that electron will accelerate between that potential difference, right? Just like we did in the photoelectric effects simulation. All right, now there's a phenomenon called Bragg diffraction, and this is exactly what we talked about a couple of slides ago, where we saw that an electron going times 10 to the 5th meters per second had a wavelength, right? A de Broglie wavelength that was on the order of times 10 to the -9, right? On the order of nanometers. Turns out this crystal has an atomic spacing, right? An aperture size for those electrons to go through that's on the order of 10 to the -8, right? So when we've got a wavelength that is the same order of magnitude as the aperture size, we should see diffraction, and we should see an interference pattern. And these 10 to the 9 and times 10 to the 8th are very close together. So we could assume that criteria is verified, and if we shoot some electrons going at like about times 10 to the 5th meters per second, we should see a diffraction pattern as those electrons travel through this crystal. Okay, after they've been accelerated, right, created in the electron gun, accelerated through a potential difference, and they hit a crystal that has an atomic structure that has gaps in it at about that size. And that's actually what they found. So there's, you can use a crystal, or you can use something with another crystalline structure like graphite. And so Davison and Germer did an experiment, and they demonstrated this for sure. And I'm going to pause this, and I'm going to ask you to watch a YouTube video that's in 2 parts attached to the Google Classroom. So please watch both of them. It's not a super high quality video, but he does have an apparatus to show this experiment and how it works and what it looks like. And again, the scientist, I think he's an Australian scientist, but he works at the U of O. He's got a U of O duck shirt on. So please pause this video. I'm actually going to cut this video, and I'm going to rejoin you in part B of this lesson after you watch the 2 attached YouTube videos that I've got for you. All right, see you soon.